One of the ways of framing a linear regression model is viewing it as an estimation of the conditional mean of our outcome given the value of our explanatory factors. So by estimating the linear regression model, we're not only estimating the association between y and x, we're also estimating the conditional mean of y given x. And because of this, we can think about the conditional mean as being a parameter in and of itself. It's the mean of the conditional distribution. And as such, we might want to conduct statistical inference on this conditional mean directly. So a linear regression model can be treated as an estimate of the conditional mean of the outcome given the predictors. We can thus conduct statistical inference on these estimates. So what are we meaning specifically by the conditional mean? Well, the linear regression model is viewed as modeling the expected value of y given x is equal to little x, and this is always going to be given by beta 0 plus beta 1 times x, right? So whatever the value of that predictor happens to be. Now, using the estimated parameters, the conditional expected outcome can be estimated, right? So what we're saying is that if you just simply replace beta 0 and beta 1 with the specific expected values of, or this estimated values of beta 0 and beta 1 rather, right? Then we're estimating the expected value of y given x being equal to little x using this format. Okay, so specifically the expected value of y given x is equal to x can be estimated, and so we can put a little hat on our expectation here. Or we can express this simply as y hat as the estimated value of our intercept plus the estimated value of our slope times by the value of x here. Now, because y hat is itself a function of two estimators, specifically of beta hat 0 and beta hat 1, right? It's a function of two estimators, which means it's a function of two random quantities, so it also has to be random, right? Y hat is going to be random based on the distributions of beta hat 0 and beta hat 1. And as a result, we can conduct statistical inference on the estimated quantity itself, on the estimated conditional mean here, by leveraging the sampling distributions of beta hat 0 and beta hat 1. So if we view our estimate here as trying to estimate this conditional mean, right, then we can actually say, well, we can conduct statistical inference, we can say form confidence intervals around that conditional mean estimate that we have using the sampling distributions of our estimators. So how is that actually going to come together? Well, we think about what is the distribution of the estimator, okay? In order to derive this, there's a few sort of important properties, and if you've seen these properties before, great, but if not, we can take them as given facts. So expectation is going to be linear, and what we mean by that is that the expected value of x plus y is always going to be the expected value of x plus the expected value of y. This is always true, and so what does that mean for us? Well, if we think about, well, what's the expected value of y hat, right? We plug in, that's the expected value of beta 0 plus beta 1 hat times x, right? And so then we can apply this linear expectation. So that's the expected value of this first term plus the expected value of the second term, right? We can pull that x out back to here, right? Because x is not random. X is just some number. We're given what x is. And so then the expected value of beta 0 hat is beta 0. The expected value of beta 1 hat is beta 1. They're both unbiased. And so now what we have is beta 0 plus beta 1 times little x. And that's exactly equal to the expected value of y given x is equal to little x. Okay, and so in this case, what we're saying is that the expected value of this estimate here, or of this estimator, is going to be exactly the true conditional expectation. So it is going to be unbiased for the truth there. Now with the variance, it's a little bit more involved. So the variance of x plus y is not in general going to be the variance of x plus the variance of y. Instead, we get the variance of x plus the variance of y plus 2 times the covariance between x and y. And so the covariance is going to give sort of a measure of association between x and y, right? And so again, if you've seen this before, great. If not, we can take that this is given fact. And so again, we can apply this exact same result to the case of y hat, right? And it's going to be a little bit more involved here, but we can walk through what's going on, right? So we have our variance of y hat. We just simply plug in our estimator here. And so now we can apply this result. That's going to be the variance of our first term, beta hat 0, plus x squared times variance of beta hat 1. Remember, whenever you're pulling a constant out front, x is a constant here. And so whenever you're pulling a constant out front of a variance term, you square it. And so that's the x squared variance of beta hat 1. And then we can do the same thing with the covariance between the two of them. And here that x comes out front because terms come out front when you're taking the covariance directly. Okay. And so then we have plus 2 times the covariance. That's just an application of this rule right here. We can then plug in all of our different values and do some simplification here, and we get sigma squared times 1 over n plus this sort of ratio of terms here where we have x minus the mean squared over the sum of xi minus its mean squared. Okay, and one way that we can actually rewrite this is if we note that this denominator here is simply n times 1 times the sample variance of x, then we can sort of rewrite this out in this sort of more compact form here. And so what we're saying is that the expected value is always going to be the true expected value, and the variance is going to be given to us by this form. And what's interesting about this form for us is that it depends on the variance of the errors, right? So sigma squared is the variance of our epsilon terms, but other than that, it only depends on things that we can actually compute from our data. So 1 over n, that's just based on the sample size. X is given to us, x bar we can calculate from our x's, right? N, again, from our sample size, and then the sample variance of x. And so if we know the mean of x, we know the sample variance of x, and we know the sample size, and then we can ultimately work out, well, what is this variance here? Okay. Now, the last thing to note, and again, if you've not seen this, we can just take this as given, is that normal distributions are going to be what we say closed under addition. And so what we mean by that is that if x and y are both normal, then x plus y is also going to be normal. Okay, and so as a result, because beta hat 1 and beta hat 0 are both going to be normal, if we are assuming either that epsilons are normal or we're assuming that we have a large enough sample size, then also y hat 1, or y hat rather, is going to be approximately normal. And so if we bring all of this together, then we can say that our distribution of the conditional expected mean is going to be approximately normally distributed with a mean equal to the truth and a variance given to us by our variance expression there. So how can we ultimately use this? And so we can think about grabbing out confidence intervals on the basis of this, right? So we have our normally distributed result here, right? So y hat is going to be approximately normal with the true mean, and then the variance given to us by this sort of simplified version of the variance formula here. Now, the trouble with using this is that sigma squared is not typically going to be known, and so we're going to have to estimate that, right? But ultimately, this is going to be able to be used for confidence intervals. So if it was known, we could use the z-based, normal-based confidence intervals, but typically it's not known, and so instead we're going to replace sigma squared with our MSE, and then rely on the Tn-2 distribution. Okay, so generally, if we want to fit a confidence interval for y hat, we take y hat plus or minus Tn-2 alpha over 2, so that's our critical value, times by the square root of our estimated standard error, right? And so the estimated standard error replaces sigma squared with the MSE, keeps everything else the same, and then we take the square root of it. Okay, and so this is going to ultimately be our format for our two-sided confidence interval. Of course, if you replace out your critical value here, you can take a one-sided confidence interval, you can take an asymmetric confidence interval. It's a standard t-based confidence interval at this point. So we can take a look at some examples of how this is actually going to work out in practice. And one of the useful things about these examples is that ultimately everything that we need is going to often be given to us through the statistical software, and so then it's just a matter of pulling the pieces together and making sense of what we're actually saying. And so in this example, we have a biologist who's studying the relationship between the concentration of a certain plant hormone, right, and the rate of root growth in seedlings. In a study of 63 seedlings, they find the following summary statistics and regression model. And so we're given these summary statistics here for our hormone concentration and our root growth rate. Right, and so this is our mean and our standard deviation. So we have a mean of 10.5, a mean of 18, standard deviation of 5.9, standard deviation of 10. We're then also told the values for our intercept and our hormone concentrations, right? We're given the beta hat estimates as well as our standard error, and we're given some information here. So the square root of our MSE is 3.14, and our R squared is 0.893. We want to estimate the expected growth rate with a 95% confidence interval for a seedling who has an auxin concentration of 12, right? And so if we think about what we're trying to do, what we want to say is, well, what is the expected value of y given x is equal to 12, right? But we're trying to estimate this, and then this is ultimately going to be beta hat 0 plus beta hat 1 times by 12, right? So that's going to give us our point estimate, but then what we're going to want to do is we're going to want to take this point estimate, and we're going to want to use our plus or minus our critical value, right? So that's a Tn-2 alpha over 2 times by the standard error. And the standard error here is going to have to take on that format for our standard error, where we take the MSE times by that bracketed term of 1 over n, and then you have x minus its mean squared divided by n minus 1 times by the standard deviation of x. And so if we think about, well, what is the information that we're actually going to be needing here, right? We need to know beta hat 0 is 1.4 and beta hat 1 is 1.5, right? So that's going to give us both of our coefficients here. We have our 12. We need to know n, but we're told directly that n is going to be 63, and so that's fine. We want to do alpha, but we know that this is a 95% confidence interval, and so remember that alpha is always going to be equal to 1 minus our confidence level, and so that's going to give us alpha as 0.05, okay, and so that's going to be fine for us there, right? We then need to know our standard error, and our standard error is going to be given to us, or requires our MSE, and so 3.14 is going to be the square root of our MSE, right? So if we just write that in here, the square root of the MSE is 3.14. Okay. We also need to know our sample size. We've already identified that to be 63. We need to know the mean of x. Remember, x is going to be our hormone concentration, so the mean is 10.5. Okay. And we need to know the variance of x. And the variance of x is going to be given to us by 5.9 squared, because this 5.9 represents its standard deviation. Okay, so then we can take all of that information, we take that all in together, and then we're going to be able to work out our point estimate and our confidence interval here. Okay, and so then we can walk through this process and actually sort of solve this with our numbers here, right? So we want to estimate the expected value of y given x is equal to 12. So we get that 1.4 plus 1.5 times 12, which gives us 19.4. For the 95% confidence interval, we have alpha equals 0.05, right? 1 minus 0.95. And we observe n is equal to 63, x bar is 10.5, the standard deviation of x is 5.9, and the square root of our MSE is 3.14, right? That's all that information that we need there. And so then ultimately we can start to pull this together, right? We want to take the n minus 2 alpha over 2 critical value. That's going to give us negative 1.9996, right? The way we get that is by using the QT function. So QT is always going to give us our critical values from our t, right? 0.05 divided by 2, it gives us our level here. Degrees of freedom is 61, okay? And so that's going to give us the value we need there. And so then if we want our confidence interval, we take our format here and we plug in, right? So we have y hat is going to be 19.4. We work that out, right? Our critical value is this 1.9996, okay? And then we take the square root of our MSE is 3.14 times by the square root of this, right? So that's 1 over n is 1 over 63. X is 12 minus its mean squared, n minus 1 times by the sample variance here. Okay. And that's going to ultimately give us this confidence interval here of 18.6 to 20.2. And so that gives us a 95% confidence interval for the rate of growth of a seedling if there's an auxin concentration of 12. Okay. Our estimate is going to be 19.4 millimeters per day, and then the rate of growth is going to be sort of falling into this confidence interval here. Okay. Take a look at another example here, and we can walk through this one a little bit more quickly because all of the pieces that we need are sort of given in the same kind of way, right? So we're going to be looking at a chemist who's measuring the mass of a chemical product that's being produced based on the mass of a given reactant. They run the experiment for 37 different settings and find the following. So our reactant mass has a mean of 11.1 and a standard deviation of 5.2. The product mass has a mean of 28 and a standard deviation of 13. Our intercept is going to be estimated at 0.73. Our reactant so our slope is going to be estimated at 2.5, right? Standard deviations of 0.229 and 0.019 respectively. Our square root of our MSE is 0.588, and our R squared is 0.998. So we want to estimate the expected mass of the chemical reaction that's produced with a 99% confidence interval if there is 8 grams of the reactant. And so what we're saying is we want to estimate the conditional mean of our mass produced given x is equal to 8. And so we take our intercept plus 2.5 times 8, and that's going to give us the expected value, the point estimate. And then when we want to get our 99% confidence interval. Well, 99% is going to correspond to an alpha of 0.01, right? We have sample size of 37. We have X bar is 11.1. We have the standard deviation is 5.2, right? And we have the square root of our MSE is 0.588. And so then we're going to plug everything there into the formula that we have for our confidence interval and work through those calculations. So what does that actually look like? We want the point estimate, right? That's going to be 0.73 plus 2.5 times by 8 gives us 20.73. We have alpha is going to be 0.01, and we're observing n is 37, x bar is 11.1, sx is 5.2, and the square root of MSE is 0.588, right? So that's all the information that we identified from those tables. That's everything that we need to solve this question here. So going forward with it, we have our t n minus 2 distribution. That's going to be t at 37 minus 2, or t 35 distribution. That corresponds to a critical value of negative 2.0301. Right? We can get this using our qt function. So qt is always going to give the critical value of the t distribution, 0.05 over 2, and degrees of freedom equals 35. Ultimately, that's going to output negative 2.0301. If we then want our confidence interval, we take our format here, right? We have y hat plus or minus the critical value times by the square root of our standard error. And so then plugging everything in, 20.73 is the estimated value, critical value, square root of our MSE, and then we take the square root of the other term here, right? We're plugging in all of the values that we have and working through, we find 20.531. Okay, and so the estimated mass is going to be 20.73 if the reactant mass is 8, with a 99% confidence interval of 20.531 up to 20.929. We can take a look at a third example here. And again, we'll walk through. It's very similar to the others, right? So we have a researcher who's interested in exploring the relationship between an individual's level of extroversion and their score on a standardized anxiety assessment. In a sample of n equals 50 individuals, they observe the following results, right? And then we are given our output for our summary statistics and our regression table. So here we have that the mean level of extroversion is going to be 3.09 with a standard deviation of 1.17. The mean social anxiety, which is our outcome, is 22.8 with a standard deviation of 5.2. Our intercept is estimated at 34. The slope is estimated at negative 3.7 with our standard error is given here. The square root of our MSE is given to us by 2.82. Our R squared value is given here. We want to estimate the expected anxiety score with a 99% confidence interval for an individual scoring 5 on extroversion, right? So we have x is equal to 5. We want to estimate the expected value of y given x is equal to 5. Okay? And so we need to sort of extract out the useful information here, right? We need to know our sample size, which is 50. We need to know the sample mean of x. We need to know the sample variance of x. We need to know both of our estimated coefficients here, and we need to know the square root of our MSE. Okay, and so then pulling all of this together with a 99% confidence interval, we're going to get alpha equals 0.01. And so then we can plug everything in as we need here, right? So we want expected value of y given x is equal to 5. And so that's going to be 34. And then note here that we are adding our slope times by x, right? But here, because our slope is negative, that's going to be 34 minus 3.7 times by 5 to give us 15.5, right? So it's the exact same as before, but we just have a negative value for our slope here. And there's no problem with that. You just subtract rather than add. Because we have our 99% confidence interval, we want alpha equals 0.01. And so we're going to observe n is equal to 50 and x bar is 3.09, sx is 1.17, and the root of the MSE is 2.82. So then to get our confidence interval here, we want to identify first the t distribution we're actually using. So that's going to be a t n minus 2 distribution, right? So a t48 distribution in this case. We want the alpha over 2 critical value. That gives us a 2.6822, right? We can get this using our qt function. Qt is always going to give us our t critical values, 0.01 over 2. That's the critical value we want with our degrees of freedom equals 48. So that will output our critical value there. And then ultimately we plug everything in to our formula here, right? So we take y hat plus or minus our critical value times by the root of our variance here, right? So that's 15.5 plus or minus our critical value times by the square root of our MSE, and then everything else plugged in here, right? So our value minus the mean, our variance is down here, and our sample size is right here. And ultimately, that gives us about 13.4 to 17.6. And so then ultimately, on this problem here, there's an estimated expected anxiety score of 15.5 if the individual's level of extroversion is 5, and we have our 99% confidence interval is 13.437 up to 17.563. The last example we'll take a look at here has a rehab clinic that wants to determine the relationship between the weekly time a patient spends in physical therapy and their improvement on a standardized mobility score. They collect data on 100 patients and obtain the following, right? We want to estimate the expected mobility score with a 90% confidence interval for a patient spending 10 hours in therapy per week, right? And so again, we're becoming sort of experts at this by now, hopefully, but we want to estimate that conditional mean given x is equal to 10, right? And so we take 5 plus 2 times 10, and that's going to give us our point estimate. We also want a 90% confidence interval. Because we want the 90% confidence interval, alpha is going to be 1 minus 90% or 10%, right? In order to plug it into the formula we have there, we need that point estimate, but we're also going to need n is going to be 100. The mean of x is 5.49, right? Because x is therapy hours, so we look at our summary statistics for that. The variance of x is going to be 2.56 squared, right? And the standard, or the square root of our MSE is 2.91. So sigma is going to be given by, sigma gives us the square root of our MSE rather, right? And so that's 2.91. And so then ultimately all of this can be plugged in directly, right? And so we can start walking through. So the expected value of y given x is equal to 10 is going to be 5 plus 2 times 10 or 25. For a 90% confidence interval, we have alpha is going to be 10%, right? And we observe n is 100, x bar is 5.49, the standard deviation of x is 2.56, and the root MSE is 2.91. So then we plug all of this in, right? We get our critical value is going to be our Tn minus 2 critical value, with alpha over 2 as the level, right? That gives us negative 1.6606. We get this using our QT function. QT is always going to give the critical values for our T distribution. So that's 0.1 divided by 2. That's the level we want. Degrees of freedom is 98. We plug into our confidence interval formula here. We get our point estimate plus or minus our critical value times the standard error, right? And so that's 25 plus or minus critical value is the 1.6606. Root of MSE is 2.91, and then we're plugging in our other values there. So 1 over 100 for one of our sample size, 10 minus x bar squared, 100 minus 1 times by the variance there, right? And so that gives us our 24 to 25.9, so 24 to 26 as our rough interval there, right? And so we can say that there's an estimated expected mobility score of 25 if the patient spends 10 hours per week in therapy. The 90% confidence interval is going to go again roughly from 24 up to 26. So in a simpler linear regression, because we have normal sampling distributions for both of our main parameters there for the slope and the intercept, this is going to give rise to a normal sampling distribution for the estimated conditional mean of the distribution. That conditional mean of the distribution can then we can get point estimates by plugging into our estimated regression model there, and then we can also get intervals around those point estimates, right? Standard confidence intervals, they're based on the T distribution, and as a result, everything that is relevant to T-based confidence intervals is going to be relevant in this case. We can look at the two the symmetric intervals that we were considering in this lecture here. But if you change out your critical values, you could get one-sided intervals or asymmetric intervals as is needed, right? And then ultimately, the values that we need to plug into that formula are going to be based on the summary statistics for x, as well as the estimated MSE from the distribution there, from the regression model itself. So all of that is going to then allow us to characterize, well, what is the conditional mean of our outcome given a value for our predictor variables, right? And so this is going to allow us to talk about that conditional distribution for specific values that might be of interest to us.